Think about a single photon. A particle of light may be left from a distant star millions of years ago and crossed an impossible emptiness just to land on your eye. Or maybe it's bouncing between the screen and your face right now, faster than anything in the universe. In all of physics, there is a rule so basic that we almost never say it loud. Elementary particles cannot be divided. You cannot halve an electron, you cannot have a third of a quark, and you cannot, under any circumstances, cut a photon into smaller pieces. It is simply not a thing that can be done. This isn't a technological limitation. It's not that we lack sharp enough scissors. It's built into the definition of what elementary means. To be elementary is to be indivisible, full stop. But a few months ago, a team of physicists, 3 researchers in Norway, asked a strange question. Not whether a photon can be divided. They knew the answer to that. They asked, what would happen if you tried it anyway? Hold on, have you even tried to cut a photon? It's light, it doesn't sit still. You can't exactly put it on a table and take a knife to it. You catch it mid-flight. You put a shutter in its path, a mirror that can switch between reflective and the transparent at insane speeds, and you time it so the shutter closes while the photon wave is still passing through. You truncate it, you slice the wave before the photon has finished being a photon. And what comes at the other side? Not a smaller photon, not a half photon, not even a photon mixed with empty space. The result is a superposition containing an infinite number of photons, a swarm, an infinity of particles boiling from what should have been absolutely nothing. From nothing. From the vacuum itself. The shutter cannot divide the photon. It stirred the empty space around it so violently that the vacuum is producing particles. The vacuum can do that? I thought vacuum was empty. Done. Nothing there. It's a conclusion that sounds completely impossible, and yet this is a direct, unavoidable consequence of the deepest rule of quantum physics. Let's back up, because to understand why this result is so strange, we have to understand what it means to be something elementary. Most things in the universe can be divided. A rock can be broken into smaller rocks. A molecule can be split into atoms. An atom can be split into electrons, protons, and neutrons. Protons and neutrons can be split into quarks. But then you hit the bottom. Quarks, electrons, photons, these are elementary particles. They have no internal structure, no smaller parts. You cannot take an electron and get half an electron. The word half doesn't apply to it. So wait, it's not just that we haven't figured out how to do it, it's that the sentence half an electron literally doesn't mean anything. It's like asking what's the north of the North Pole? The question itself breaks. And for a century, that was the end of the story. Elementary particles are indivisible. Move on. But here is where a tiny crack appears in the foundation. Saying a photon is indivisible is one thing. But a photon isn't a tiny marble sitting still. A photon is a quantum object. It has a wave function, a spread out description of where it might be and what it's doing. A single photon traveling through space is not a point. It's an extended thing. It has shape in time. Wait. The photon has a shape? I didn't even know that photon could have a shape. I thought it was just a dot, a flicker, or something like that. That's the classical intuition. But quantum mechanically, a single photon is a pulse, a wave packet with a beginning, a middle, and an end. It takes a finite amount of time to pass through any given point. Which means, in principle, you could try to interact with only a part of that shape. You could place something in the path that turns on and off so fast that it catches only the leading edge of the photon's wave before the rest of it has arrived. So, you're trying to catch it in the middle, like closing the door while someone is still walking through? Exactly. Only this door switches between the mirror and the window, and the someone is a single quantum of light. Let's make this concrete. The paper, and I should say, this paper is now accepted for publication in Physical Review Letters, one of the most prestigious physics journals in the world. The paper describes a thought experiment, not something they built in a lab yet, something they worked out mathematically from equations of quantum electrodynamics. So they didn't actually do it, they just figured out what would happen on paper. On paper, but the paper is equations and equations don't lie. Quantum electrodynamics is one of the most precisely tested theories of all of the science. If the math says something happens, the universe takes it seriously. Imagine a single photon traveling through space. It's described by a wave function, a smooth pulse of electromagnetic possibility spreading as it moves. In front of this photon, you place a special kind of mirror. This mirror is connected to a shutter mechanism that can switch on and off between two states, reflective and transparent. And it can do this switching at incredible speeds. How fast are we talking? Fast enough to switch a photon moving at the speed of light is still only halfway through. A photon is about a micron length in the direction it's traveling. Light crosses a micron in about 3 femtoseconds. Your shutter has to be faster than that, so impossibly fast for now. And in thought experiments, theoretically allowed is all you need. Now you time it perfectly. The shutter is transparent as the leading edge of the photon's wave arrives, so the front part passes through. Then, while the photon is still in transit, the shutter slams into reflective mode, blocking the trailing part of the wave. What you have done is truncate the photon. You have taken a single elementary particle, the indivisible quantum of light, and you sliced its wave function in time. So on one side you have a part of a photon and on the other side you have the rest of it. That's what the common sense says, and the common sense is about to completely shatter. Here is what the mathematics says comes out the other side. On the left side of the mirror, the side where the transmitted part of the wave went, you do not find a half-photon. You do not find a photon with reduced energy. You do not find a photon mixed with vacuum, like 70% chance of a photon and 30% chance of nothing. What you find is a quantum state that contains a superposition of photon numbers from 0 to 1 to 2 to 1,000 to a million, all the way up to infinity. Wait. You started with one photon, and now you're talking about infinite photons. That doesn't make sense. Where did they all come from? This is where it gets deep. They come from what we think as nothing. The quantum vacuum, the empty space, is not actually empty. According to quantum field theory, even in the complete absence of particles, the electromagnetic field is never truly zero. It fluctuates. Tiny, temporary ripples of energy appear and disappear constantly, everywhere, all the time. Usually, these fluctuations are just fluctuations, virtual particles that exist for the briefest possible instant and then vanish, leaving no trace. They are the background noise of reality. Okay, but virtual means not real, right? They are not actually there. They are more like math ghosts. That's the usual story. They are the bookkeeping tools. They appear in the equation and cancel out before anything measurable happens. But what this paper shows is that the shutter changes that. When you slam a mirror through a photon's wave at the right moment, you just don't truncate the photon. You violently disturb the electromagnetic field in that region. And those fluctuations, those ripples in nothing, get stirred up, excited, promoted from the virtual to real. The knife didn't divide, the knife created a whole new set of particles. So nothing isn't nothing. And if you poke nothing hard enough, it gives you infinity. That's completely insane. Let this sink in. You start as a photon, you try to slice it in half, and the universe responds by giving you an infinity. Now I've told you the paradox, but there's a second layer to this paper that makes it even stranger, and it might be the most important part. The researchers then asked, what does this infinite photon actually look like if you measure it? If you put a detector on the left side of the shutter, what do you see? And what about the right side? Okay, but if there is actually infinite photons there, wouldn't that be blinding? Like, shouldn't we be noticing an infinity amount of light? You'd think so, But here's what the mathematics says. If you measure the state on the left side of the transition, the side where the photon was transmitted, the measurement looks exactly like a single photon, identical, indistinguishable. There's no local measurement you can perform on that side that would tell you anything strange has happened. But that's not true. We know that there is infinity stuff in there. The math just told us, so why can't we see it? Because the infinity doesn't live on the left measurement, it doesn't live in the right measurement, it lives in the gap in between. And on the right side, the side where the photon was blocked, the measurement looks exactly like vacuum, empty space, nothing there. So where did the infinity go? Is just invisible? Hidden in plain sight. All the strangeness, all the infinite photon numbers, all the superposition, all the vacuum generated particles is confined to narrow transmission region between the two sides. The paper calls this local equivalence. To the left side, it's locally equivalent to a single photon. To the right side, it's locally equivalent to a vacuum. But in that thin slice between them, that's where the infinity lives. Think about what this means. You can have a quantum state that, when you look at it from the outside, from the either side, appears completely mundane. A photon here, nothing there. But the full quantum description of what's actually there contains infinite complexity, an endless swarm of particles that no local measurement can detect. This is where the common sense completely shatters. The universe lets you try to cut the uncuttable. It just doesn't give you pieces, it gives you infinity, and then it hides it in a place so narrow, so localized, that from the outside, everything looks perfectly ordinary. So, what does that actually mean beyond the mathematical curiosity, beyond the mind bending paradox? What have we learned? I think there are three things. First, the quantum vacuum is not passive background. It's not an empty stage on which particles perform. It's an active participant. It can be stored, it can be made to produce real particles. The boundary between something and nothing is far thinner than we imagined. So the universe is basically sitting on a powder keg of stuff that could become real at any moment. That's not far off. Nothing is always just a disturbance away from becoming something, infinite something. Second, the concept of elementary may need revision, not in the sense that elementary particles can be divided, they still cannot, but in the sense that single elementary particle, when you interact with it in wrong way or the right way, depending on your perspective, doesn't stay elementary. The quantum state it becomes is not particle at all. It's a superposition spanning every possible photon number from 0 to infinity. So what is it then, if not particle anymore? It's a quantum state, a new kind of thing that doesn't fit into old boxes. Elementary turns out to be fragile. Not wrong, but fragile. A photon is indivisible. Only if you leave it alone, try to divide it, and becomes something else entirely. Third, and this is the deepest, this result points to something about the relationship between the information and locality in quantum system. How can a state contain infinite complexity while appearing simple to every local observer? But if it's not on the left side and not on the right side, where is it? That's the right question. The infinity isn't stored in any one location. It's stored in the correlations between the location. The relationship between the left and the right, that's where the information lives. And that's the theme that shows up everywhere else in physics. In black hole physics, there is a holographic principle. All the information that falls into the black hole might be encoded in its surface, not inside it. In quantum entanglement, the interesting thing about two entangled particles isn't either particle alone, it's in their connection. This truncated photon seems to be another example of that same deep pattern. The interesting physics isn't in the part, it's the connection. So it's not about what things are, it's about how they are connected to other things. Exactly. And the team behind this paper has said they plan to explore what happens with more than one photon next. Two photons, a stream of them. What happens when you truncate something even more complex? The mathematics suggests the result could be even stranger, new kind of quantum states, new ways for the vacuum to respond. We are now ready to take that final leap. There is a moment in every area of physics when you realize the map you have been using, the one that's guided you perfectly for decades, has an edge. And at that edge, there is a sign. It doesn't say, "Here be dragons." It says something more interesting. It says, "The rules you know don't apply here. You are going to need a new map." So, where do you even get a new map? You ask a question nobody thought to ask. What happens if I close the shutter on a photon before it finished arriving? The indivisibility of elementary particle is one of those old map rules. It's been true for a century. It's in every textbook. And in a narrow practical sense, it's still true. You cannot isolate half an electron in a lab. But what this paper shows, what the mathematics forces us to confront, is that the attempt to divide the indivisible doesn't just fail, it produces something entirely unexpected, something that reveals the quantum vacuum as a creative force, something that hides infinities inside ordinary looking measurement. This isn't just a mathematical quirk. It points to fundamental nature of reality, the boundary between one and many, between something and nothing, between particle and swarm. These boundaries are not as solid as we thought. They flicker, and in the right circumstances, under right kind of disturbances, one becomes infinity. Nothing becomes something, and the indivisible becomes something that we don't have a word for yet. Something that we don't have a word for yet. What was the universe before we knew this? The honest answer is the same as it was before. The mathematics has always been there, buried in the equations of quantum aerodynamics. We just hadn't asked the question. Nobody had thought to put the shutter in the path of a photon and ask, what if I close it before the light has finished arriving? It seems so obvious once you hear it. Like, of course, someone should have asked that. Now someone has, and we have a new signpost at the edge of the map. So let this sink in. Every photon hitting your eye right now, every particle of light that enters your consciousness carries with the possibility of infinity. Try to cut it, and it would break. It will swarm. Hidden inside the simplest, most indivisible thing in the universe is a door to infinity. All you have to do is to try to close that door at exactly the wrong moment.